Our universe, the galaxies, the solar system, our home planet Earth. Land, sea, air, life. Where did they all come from? Look up into space from our planet, and what you see is a vast cosmos, teeming with billions of stars and galaxies. Turn back the clock over 13 billion years, and our universe was a very different place. Back then it was so small that it could fit inside the palm of your hand. From this infant universe, everything would be created: stars, galaxies, and the building blocks of life itself. The calcium in our bones, the iron in our blood, the atoms for the air we breathe, the water we drink, the raw materials for our cities and machines. Naked science takes a journey through space and time to discover how the universe was born and how it created everything in our world, and how eventually it will die. Everything we see around us is made of matter, atoms, and molecules. Take this car. It's a 1956 Ford Fairlane convertible. It's constructed from many different materials, like steel, rubber, and glass. Go deeper, and these materials are made up from combinations of elements like iron, silicon, chromium, and carbon. Each and every atom that makes up this car were created by our growing universe. Physicist Lawrence Krauss studies how the atoms we see on our planet have come to be here.
We really are part stardust and part Big Bang dust. Most of the atoms in our body are from the cores of stars, but some of them have been around since the earliest moments of the Big Bang. So we really are truly cosmic individuals.
Each and every atom was created over billions of years as our universe evolved.
So when we look at this car, of course, all the atoms in this car came from stellar explosions, from supernova processes, and from stellar evolution. But they were created at different times during the evolution of the universe.
To understand how the universe made all the raw material we see here on Earth, we need to take an incredible journey and travel back through space and time to the moment our universe was born. In the beginning, there was nothing. No space, no time. And then there was light. Suddenly, a tiny speck of light appears. It was infinitely hot. Inside this tiny fireball was all of space. This was literally the beginning of time. The cosmic clock was ticking. Time could flow, and space expand.
At the earliest moments of the Big Bang, if you take it back to t equals 0, everything in our universe, everything we can see, all the matter and all the energy in all of the galaxies was once contained in a region smaller than the size of a single atom today.
The idea that our universe was once tiny originated from the brilliant work of American astronomer Edwin Hubble. Back in the 1920s, most astronomers believed that everything visible in the night sky were stars, and they were part of our galaxy, the Milky Way. But Hubble wasn't convinced. He studied a swirling cloud of light called the Andromeda Nebula and showed that it was a star city, another galaxy, far outside of our own galaxy. He showed that these other galaxies were speeding away from ours, and the further away they were, the faster they seemed to be moving. The universe was expanding. And if the universe was expanding, then at some point in the past, it must have been smaller. Much smaller. and that it must have had a beginning. The idea of the Big Bang was born. Theoretical physicist David Spergel is a Big Bang expert.
The Big Bang theory is not really a theory of how the universe began. It's really a theory of how the universe evolved.
No one knows exactly what happened during the Big Bang, but scientists do know that a fraction of a second after the universe was born, this tiny, super hot fireball was already starting to expand.
We don't know how the universe began. So we start our story when the universe was a billionth of a billionth of a billionth of a billionth of a minute old. Pretty young. The universe was the size of a marble.
Less than a trillionth of a second after the Big Bang, the marble-sized universe was very unstable and underwent an enormous growth spurt.
During this period of incredibly rapid expansion, space itself was expanding faster than the speed of light.
In the same way that this hot glass ball inflates, so did the baby universe, expanding in all directions at once. And as it expanded, it cooled. A trillionth of a second after the Big Bang, the universe was small enough to fit inside the palm of your hand. A tiny fraction of a second later, it was the size of Mars. Another fraction of a second, and the baby universe had grown to 80 times the size of the Earth. A trillionth of a second after the Big Bang, and our newborn universe was still expanding, but it didn't contain matter. It was pure energy. Einstein's famous equation, E equals mc squared, showed that mass and energy are interchangeable. It gave us the knowledge to build weapons of mass destruction. It also revealed how the universe created the first matter. When a nuclear bomb explodes, a tiny amount of matter is annihilated and converted into energy. In the baby universe, the exact opposite happened. It converted pure energy into particles of matter. But there was a problem. The universe created both matter and its arch-rival antimatter, and when these two met, they obliterated each other. The infant universe was a war zone, a battle to the death between matter and antimatter. If they mutually annihilated each other, the universe would remain full of energy, with no galaxies, stars, planets, or life. Fortunately for us, there was an imbalance. For every 100 million antiparticles formed, there were 100,000,001 particles of matter.
But there was that one extra particle of matter left over in each volume, and that was enough to account for everything we see in the universe today.
This tiny imbalance led to all matter we see in the universe: galaxies, stars, planets, even convertibles, and ourselves. Astrophysicist Carlos Frank from Durham University in England explains.
We are a little bit of debris left over from the annihilation of matter and antimatter. We're the leftovers of that process. If the universe had not developed this slight asymmetry between matter and antimatter, the universe would have been completely boring. There would be no structure, there would be no galaxies, there would be no planets.
Quite what this newborn universe was like has challenged cosmologists since the Big Bang was first put forward. Now, in one of the biggest laboratories on Earth, they are able to recreate conditions that almost certainly existed an instant after the Big Bang. It's called the Relativistic Heavy Ion Collider, RHIC for short, and it's located at the Brookhaven National Laboratory on Long Island. It's like a time machine, taking us back to 10 millionths of a second after the Big Bang. Here, scientists like Todd Satogata accelerate subatomic particles close to the speed of light and then smash them into each other. The particles race around this 2.5-mile circular tunnel in opposite directions 78,000 times a second, and then collide inside this giant detector bigger than a 3-story house. When they smash into each other, they generate incredible heat, just like the real infant universe.
We believe the early universe was extremely hot, billions of times hotter than the center of the sun. And what you're doing when smashing these nuclei together is melting matter, creating matter hot enough to give us a glimpse of what the very early universe was like.
When the particles collide, they break open and throw out a shower of even smaller particles. It's a bit like discovering what cars are made of by watching them smash into each other.
You can race two cars together and smash them into each other head on. And when you do that multiple times, you start to see different patterns coming out. A tire comes out here, a radiator comes out there, and before long you can start to conclude that a race car is made up of these certain pieces.
What the scientists at Brookhaven have discovered is that within these superheated collisions, a completely new form of matter appears. And this matter contradicts the previous theories on the nature of the early universe. Because it's not a gas, it's a liquid. It was super hot, 100 million times hotter than the surface of the sun. There was so much energy inside the young universe that the particles vibrated so fast that it had no stickiness. There was no friction, and it flowed perfectly.
This liquid is perfect. It has no viscosity. In some sense, it would be the perfect motor oil, except it's 1 trillion degrees hot.
Inside the collider, this amazing liquid universe exists for only a tiny fraction of a second. The Brookhaven scientists have succeeded in recreating conditions that existed over 13 billion years ago. Despite the universe being a perfect liquid, it was in turmoil. It was full of subatomic particles smashing into each other, releasing more and more energy. There was so much energy that unless the particles slowed down, they would never bond and create atoms, the building blocks of matter. And the universe would never create the galaxies and stars, or even us. The universe is now 1/1,000,000th of a second old and has expanded from smaller than the size of an atom to 8 times the size of the solar system. After the incredible turmoil of the first millionth of a second, the universe was now relatively calm. Over the next 3 minutes, the expanding cosmos cooled sufficiently for protons and neutrons to bind together and form the first atomic nuclei, hydrogen and helium. These were not yet proper atoms. They were missing a vital ingredient, the electron. In the hot baby universe, there were plenty of electrons around, but there was still so much heat and energy, the electrons were moving too fast to form bonds. And it would stay that way for over 300,000 years. 380,000 years after the Big Bang, the universe had expanded to the size of the Milky Way. It had cooled from billions of degrees Fahrenheit to a few thousand. As it cooled, the electrons slowed down. The universe was now ready to make its first true elements. One of the scientists who discovered this critical moment in the story of the universe was Arno Penzias. 1963, 30-year-old Penzias and his 27-year-old colleague Robert Wilson began work on a new antenna in New Jersey. Initially, they were only studying cosmic radio waves, but they would stumble on one of the greatest discoveries of all time. As they started to test their equipment, they detected an unexpected background noise.
It was additional signal, and it appeared to be coming from the sky. We eliminated very carefully the ground, even the solar system, because we did this winter to summer, seasonal variation, man-made sources of equipment. All these things were eliminated.
In desperation, the two scientists began to wonder whether the strange signal might have another, more earthly origin. They found there were pigeons roosting in the antenna, and it was covered with droppings. They wondered if the pigeons were the source of the strange signal. There was only one solution. The droppings and the pigeons would have to go.
We finally got around to removing the pigeon droppings. We also had to remove the pigeons. That was a difficult problem because they turned out to want to come back, and we mailed them off to another site.
But even with the troublesome pigeons gone, the mysterious signal would not disappear.
And so we were left with the almost inescapable conclusion that this radiation was coming from the sky. I could not account for it.
The strange signal detected by Penzias and Wilson would turn out to be one of the most important scientific discoveries of all time. But the explanation for their mystery background noise starts not with sound, but with the birth of light. We usually take light for granted. But in the early universe, 13 billion years ago, we would see nothing at all. Light was trapped. The universe was foggy. Imagine a flashlight beam in a fog of smoke. The light bounces back and forth between the smoke particles and is trapped. In the hot baby universe, a dense fog of electrons block the light from escaping. But as the universe continued to expand and cool, the electrons slowed down. Protons then grabbed these calmer electrons to form complete atoms of first hydrogen and then helium. The universe was suddenly much less crowded with electrons. The fog lifted, and light was no longer trapped. It hurtled out across the universe, creating a blinding burst of light.
Had we been there, we would have suddenly seen this opaque universe become transparent. Suddenly the fog would lift, and we would see a flash of light coming from everywhere around us. It must have been a spectacular moment.
Over time, this burst of light dimmed and cooled and became microwave radiation. It was this faint 13-billion-year-old microwave signal that Penzias and Wilson picked up on their antenna. What they heard was the quiet echo of the moment the universe formed the first atoms.
It's really the light from the origin of the universe. If you have an old FM receiver, if you tune between channels, turn the knob, and it doesn't capture it and pop to a station, you get to a part where there's none, you hear a that's what we call noise. If you have a good radio set, 0.1% of that is actually the sound of the Big Bang.
And we can also see the moment when the first elements were created. If our television is not tuned to a station, a tiny fraction of the noise is radiation from 13 billion years ago. But this radiation is not the only reminder of the birth of the universe. Even the water we drink is a memento.
And it's kind of amazing to think that every time we take a drink of a glass of water, we're drinking in atoms that have been around since the Big Bang, the hydrogen atoms.
Over the next millions of years, the young universe continued to expand, cool, and get dark again. So far, the universe had only made hydrogen and helium atoms. But the world we live in is made from more than 100 different kinds of elements. Without them, the universe would remain a very boring place, made up of only gas, a place where complex matter, like planets, cars, and people, could never develop. The universe needed to get hydrogen and helium atoms to fuse. And to do that, it needed to make stars. The universe was now 200 million years old, and billions of light years across. Its temperature had dropped so far that it was colder than liquid nitrogen, minus 367 degrees Fahrenheit. It was also dark. It would have remained a very gloomy place full of gas, but without galaxies, stars, or planets, if it hadn't been for one thing. The baby universe wasn't born perfect. Carlos Frank has created an amazing 3D simulation of how the early universe evolved. It shows that when the universe emerged from the Big Bang, it was uneven.
Little cracks appeared, which were very, very, very tiny, very, very small. And it was this rush in the face of the baby universe that later developed into the patterns that we see in the galaxies today.
Without these cracks, the universe would have been a very dull place. The first clues as to how these cracks developed into galaxies and stars came when other scientists started to examine the Big Bang radiation first discovered by Penzias and Wilson.
So what Penzias and Wilson saw was this radiation was, as far as they can tell, uniform. What cosmologists then did for the next 25 years was work very hard to try to find tiny variations.
And find them they did, using WMAP, a space probe designed to detect and analyze in detail variations in the background microwave radiation. Launched in 2001, the $150 million probe was fitted with some of the most sensitive instruments ever carried into space. Our eyes detect only visible starlight, but WMAP can tune into the invisible microwave radiation. Once in orbit around the Sun, it picked up the faint radiation that has been rippling around the universe since the dawn of time.
So when we look at the cosmic background radiation, we're looking at this radiation that's been streaming towards us since 500,000 years after the Big Bang.
Initially, the microwave universe looked very dull and seemed to be the same everywhere. But when WMAP turned up contrast, the results were spectacular. The baby universe wasn't smooth and boring at all. It was full of fluctuations.
These tiny fluctuations tell us what the variations in density, how much stuff there is, and how it varies from place to place. These denser regions are going to collapse to form clusters of galaxies and superclusters and galaxies themselves. These low-density regions, these will grow and become the empty regions between galaxies. So this picture really is our connection between the universe when it was a baby, 500,000 years old, to the universe today, 13.7 billion years old.
These tiny imperfections in the fledgling universe would become galaxies and stars.
And this is one of the most amazing propositions in physics. The idea that galaxies like a Milky Way that contain 100 million stars once began life as a tiny little crack in the fabric of the universe.
The material in these cracks was filled with swirling clouds of hydrogen atoms. The voids between the clouds grew bigger and bigger. The gas clouds got denser and hotter. Gravity pulled the gas clouds together on filaments, like beads on threads of a web, cosmic web. Where the giant filaments formed large globs, stars and galaxies would grow.
As the universe evolved, gases were able to condense into clouds, which collapse to form stars. The stars settle into a rotating disk that was later to become a spiral galaxy like the Milky Way.
Over millions of years, the hydrogen atoms clumped together and heated up. The atoms began fusing and releasing energy, and the gas clouds started to burn brightly. Eventually, a star was born. All over the universe, millions of stars ignited for the first time.
The appearance of the first stars would have been a truly spectacular event. Had we been there, we would have really seen fireworks. Individual, enormous flashes of light generated as the stars are born and burn themselves out.
the universe has expanded many trillions of times its original size. It was full of newborn stars made of hydrogen and helium. These young stars were nothing like our own sun. They were very unstable. But it was their instability that would make the universe a more interesting place, because deep inside each new star, something amazing was happening. They were creating new elements. The idea that stars build atoms came from the British astrophysicist Sir Fred Hoyle, one of the greatest astronomers of the 20th century. Hoyle didn't believe that the universe began in a single explosion. In fact, he coined the name Big Bang as a term of derision. Hoyle wanted to know where the elements heavier than hydrogen and helium came from. He figured out that stars acted like nuclear reactors, working a bit like a hydrogen bomb in slow motion. But many billion times more powerful, and their nuclear waste was new elements. But it would take years before scientists were able to confirm his theory by analyzing the light from stars. Each element emits a light at a particular frequency when heated up. Imagine a sodium street lamp. It emits light of a yellow color specific to sodium. It's the same with stars. Take our sun. If you break the light down into a spectrum, you can see lines like a barcode corresponding to the elements. Each element has specific colors, helping scientists identify elements like hydrogen, which emits mainly red light.
We are go for main engine
In
start.
1990, NASA launched the Hubble Space Telescope to unravel some of the mysteries of our early universe.
And liftoff of the Space Shuttle Discovery with the Hubble Space Telescope, our window on the universe.
Hubble promised scientists unprecedented views of the young universe. It would be able to look back through space and time and examine early stars to discover if they were making new elements. But the dream soon turned into the worst nightmare. After it was launched, they discovered that Hubble's mirror was distorted. It saw everything out of focus. It needed corrective lenses. And the only way to fix it was to send up another space shuttle. One of the repairmen was astronaut Jeff Hoffman.
We were working with a $2 billion telescope, and the last thing we wanted was to break something and leave it worse off than when we got up there.
First, the crew of the rescue mission had to capture the crippled telescope. Then execute a repair mission unprecedented in the history of spaceflight. First, they had to open the access doors on the side of the telescope.
The one thing about working on Hubble that is very different from working on a car is you look over your shoulder and there you are in space. The Earth is going by below you, the stars above you.
The astronauts had to carry out fine, detailed work in the most difficult conditions.
When you're working in a spacesuit, your hands are encumbered by thick, stiff gloves. It's sort of like working in ski mittens, and it was quite a challenge.
All went well until Hoffman attempted to close the huge access doors.
I just had to close up the doors, and when I went to close them, they wouldn't close properly. The doors were somewhat warped, and it took a while for it to sink in. This was very serious. If you can't get the doors closed, you lose the telescope.
Using improvised tools, Jeff and a colleague were finally able to close the doors. It took the team 5 days to repair the stricken telescope. Cosmologists around the world held their collective breath. They waited to see if the most expensive telescope ever built would deliver what its designers originally promised.
I well remember New Year's Eve, 1993, December 31st, when my phone rang, and it was an old friend who worked at the Space Telescope Science Institute in Baltimore. He said, "Jeff, do you have any champagne left over from your party?" I said, "Yeah, we still have a half bottle in the refrigerator." He said, "Well, crack it open again and drink a glass because we got the first picture back and Hubble works."
This is what Hubble saw. The images were beyond anyone's wildest dreams. Hubble captured the final moments of a star's life when it explodes and blows off gas and dust. It also captured interstellar nurseries of newborn stars, exploding into life billions of years ago, and dark pillars of cosmic dust, millions and millions of miles long, ready to spawn a new generation of stars and planets.
I guess it's hard to surpass the famous pillars of creation in the Eagle Nebula, where you actually see the birth of stars. I mean, it's almost biblical. Let there be light. And I still kind of get goosebumps when I look at it.
But Hubble's true moment of glory was still to come. Over a 10-day period in 1995, the mission controllers pointed the telescope at a distant empty patch of space. What emerged was the deep field image, a tapestry of distant galaxies. Hubble was looking back in time to some of the first galaxies and stars created.
It revealed thousands of galaxies that hadn't been seen before. So the universe became, to our consciousness, far richer after the Hubble Deep Field.
It showed for the first time faint images of galaxies formed just 1 billion years after the Big Bang. Scientists then examined the spectrum of light from these distant stars and showed that these early galaxies had already created elements heavier than hydrogen and helium. Sir Fred Hoyle may have been wrong about the birth of the universe, but he was absolutely right about the stars. The early stars acted like giant thermonuclear reactors, creating new elements.
You can think of the creation of all the elements in this room as, in some sense, like a car assembly line. Because in a car assembly line, each part is sequentially added to the vehicle until it's complete.
Fusion reactions inside these young stars released enormous amounts of energy and heat, which forced atoms to fuse to form new, heavier elements, one after the other. 3 helium nuclei combined to form carbon. 2 carbon nuclei fused to form magnesium. Magnesium to form neon, and so on over a period of hundreds of thousands of years, until silicon fused to form iron. Iron is a very special atom. The protons and neutrons inside its nucleus are very tightly bound together, so that even the extreme temperatures inside the stars couldn't get it to fuse into heavier elements. It resolutely stays iron. It was the end of the road. The production line of element building shut down. But our universe was still not complete. There were all the ingredients to make a glass of water, and some of the elements to build much of our convertible. There were also quite a few of the ingredients to make a human being: the oxygen we breathe, the calcium in our bones, and the iron in our blood. But there still weren't any of the vital ingredients like chromium for our car fender, and some metals like zinc that our bodies can't survive without. The universe was about to enter a super creative phase where it produces all the elements heavier than iron. To make the missing pieces in our birth of the universe jigsaw would take some of the most powerful explosions the universe has ever seen. Our universe has already celebrated its 500 millionth birthday. There are still another 13 billion more to go before humans appear on the face of the Earth. Giant new stars have made many of the elements in the world we see around us. But some vital elements are still missing. Heavy metals like chromium and zinc, and expensive ones like gold and platinum. To finish the job, the universe conjures up the most amazing phenomena since the Big Bang: massive exploding stars called supernovas. When the giant stars that made the lighter elements ran out of fuel, they collapsed in on themselves, creating incredible amounts of energy and enormous explosions. These explosions were so powerful, they could fuse elements even heavier than iron and restart the element production line. Tony Metzacappa from Oak Ridge National Laboratory in Tennessee believes that without exploding stars, life itself would not exist.
Life as we know it certainly would not exist were it not for core collapse supernova events. They are very clearly one of the key links in our chain of origin from the Big Bang to the present day.
One of the most recent and biggest supernovas closest to our galaxy was seen in the southern hemisphere in 1987. When a supernova like 1987A explodes, it emits light containing the signatures of the elements within it. By examining this spectrum of light, scientists can calculate what elements are being forged inside the exploding star. Michael Smith from the Experimental Astrophysics Group at Oak Ridge then recreates these events inside his own star laboratory. In this 100-foot tower, he accelerates and smashes individual particles into each other, just like inside a supernova.
These subatomic nuclei are the ones that are absolutely crucial in the formation of the heaviest elements. So the idea is to measure exactly how fast these nuclei will fuse together in the laboratory, and then translate that information into how fast they'll fuse inside exploding stars.
When the particles collide inside the accelerator, they generate enormous energy. In these extreme conditions, the particles fuse.
And then you can bring other particles in and they will fuse. And we believe that exploding stars are just right to form elements much heavier than iron, going all the way up to the top of the periodic table.
Using the data from these experiments, Tony Metzacappa has created a model of how these massive exploding stars turn into heavy element factories.
Massive stars, they evolve to an onion-like configuration at the end of their lives. They have an iron core, and outside of the iron core are layers of successively lighter elements.
Inside the iron core, the temperature rises to 8 billion degrees, nearly 300 times hotter than the center of the sun. It is so hot that the iron atoms that have sunk to the star's core are torn apart. The core destabilizes.
The cores then collapse on themselves in a fraction of a second. The collapse proceeds to very, very high densities.
The core collapses at speeds of more than 43,000 miles per second. A volume the size of the Earth crunches down nearly 6 times the size of Manhattan in an instant. The core becomes super dense.
If one were to take 1 cubic centimeter of that matter, that would be the size of a sugar cube. That sugar cube would be so dense that it would weigh as much as the entire human race.
The core rebounds like a compressed rubber ball and launches a massive shockwave. The shockwave hurtles out, smashing through the different skins of the star. As it punches through the outer layers of the star, the energy generated restarts the element production line. Atoms are smashed together to make brand new, heavier elements, all heavier than iron. Then the star explodes, and the shockwave pushes the shrapnel-like debris outward, further and further into space.
In a very real sense, our lives depend on the stars in the universe. Without their lives and deaths, we would not be here today.
These astonishing images taken by the Hubble Space Telescope show the aftermath of these giant explosions. Nebulae, giant clouds of debris thrown off by exploding stars. Swirling inside are big new atoms, gold, silver, zinc, and lead. Without supernovas, our world would be a very dull place and possibly lifeless.
So I'm sure that Paris Hilton doesn't wake up every day thinking about this fact, but really, if it weren't for exploding stars, those 200 million stars that exploded so we could be here today, she wouldn't have anything to wear. So if it weren't for those supernova explosions, there wouldn't be any bling.
9 billion years after the Big Bang, and all the ingredients are in place for life as we know it. The universe has grown up into a vast, complex place made up of billions of galaxies and uncountable stars. In a quiet corner of the Milky Way, a mass of dust and gas begins to accumulate. It's full of the rich debris left over from one of the massive supernovas. And when it reaches a critical mass, it begins to burn brightly. A star is born, our own star, the Sun. What's left over forms a disk of swirling debris in orbit around the new star. The gas and dust that make up this ring collide, pulled together by gravity. The clumps of dust and gas become bigger and bigger. Planets form. One of these planets is our Earth. Over the next 500 million years, our planet slowly generates a protective canopy of gas, the atmosphere. The first life appears, just single cells at first. But as the eons pass, those tiny single cells evolve into plants and animals, and eventually humans.
We tend to disassociate ourselves from the universe, but that, of course, is completely wrong. We are a vital part of the cosmos. And so when we talk about the origin and evolution of the universe, we're actually talking about the origin and evolution of ourselves.
Everything we can see on our planet was either made in the Big Bang or inside a star. Scientists like Krauss believe they now know the genesis of every atom that has created the world we live in.
These atoms have been around since the dawn of time. And when I was young, my mother used to tell me, "Don't touch that, you don't know where it's been." And she would have been amazed.
But this is not the final chapter in the story. After almost 14 billion years, the universe has really only just gotten started. Now we take a journey into the future to see how it all ends. The universe we live in is nearly 14 billion years old. It has created the raw materials for everything we see around us: the stars, the planets, trees, cities, automobiles, even us. Our world is complete, but the universe is still evolving. Scientists have come up with many theories on how it will end.
We know our universe began in a Big Bang. What we don't know yet is what the future of our universe is going to be. Our universe may end with a bang or a whimper or something even more exotic.
One theory suggests that our universe will run out of steam and stop expanding. Every star, galaxy, and planet, every atom will start to collapse, ending in a single super-dense pinpoint known as the Big Crunch. To find out if the universe really is going to crash back in on itself, scientists first need to discover if it's still expanding or if it's slowing down. Astrophysicist Saul Perlmutter studies the death of the universe by finding beacons in space, exploding stars called Type 1a supernovas.
If you have enough of these exploding stars, these supernova, that you've measured their brightness, the ones that look fainter and fainter and fainter must be further and further and further away. And so you have some supernova that are a little bit brighter, they're more nearby, some that are a little bit fainter, so they're a little bit further, and some that are very faint, so they're very far away.
Type 1a supernovas are similar to the supernovas that created the heavy elements. They differ in one important fashion. They always explode with the same exact brightness. This is because they are created in the same way. Two stars circle each other, held together by their gravitational attraction. One is shriveled and super dense, glowing with white heat, a white dwarf. The other star, has bloated to an enormous size. It's a red giant that is burning the last of its fuel. As the two stars orbit each other, the white dwarf sucks gas from its companion and begins to grow year after year. When it is precisely 1.44 times the mass of our Sun, the white dwarf crumples, collapses, then explodes, releasing a blinding burst of energy. Every Type 1a supernova explodes at the same tipping point, and so are equally bright and visible across the vast distances of the universe. Perlmutter needs to find hundreds of Type 1a supernovas and then measure how fast they are moving away from us. He links up the most powerful telescope on Earth with the most powerful in space. Using advanced cameras on the Hubble Space Telescope and a giant telescope officially known as the Very Large Telescope, or VLT for short, he hunts for supernovas. Once Hubble has detected a particular light source, colleague Chris Lidman at the VLT analyzes the object to see what it's made of and make sure it's a Type 1a supernova.
This object is a distant galaxy, and next to it is what we believe is a distant supernova. The next crucial step is to understand what type of supernova this is.
The VLT breaks down the light from the object into its spectrum.
You want to be able to break up its light into a spectrum and look for the very characteristic fingerprint that you would see if it really were a Type 1a supernova.
The light emitted from this particular supernova reveals that it's a Type 1a. Lidman can now calculate how far away this supernova is.
The supernova exploded about 7 billion years ago.
By comparing the positions and dates of all these supernovas stretched over space and time, Perlmutter can calculate whether the universe is slowing down. His results are a shock. The expansion of the universe isn't slowing down at all.
When we began the project, of course, the goal was to find out how much the universe was slowing down. Now, when we actually started looking at the data, it looked like the universe wasn't slowing enough to come to a halt. And in fact, it wasn't slowing very much at all. And in fact, when we finished the analysis, it looked like it wasn't slowing, period. It was actually speeding up in its expansion.
Perlmutter's astounding discovery means that the universe will not grind to a halt, then crunch back down into a pinhead of superdense matter. Quite the opposite. It will continue to expand faster and faster. Our universe is literally flying apart.
The expansion of the universe will accelerate at ever faster and faster rates until literally everything will get ripped apart. Not just galaxies, but eventually matter, the Earth, all the objects, stars, the Earth, planets, people, atoms, in a finite time would get ripped apart.
Long after our sun has burned out, 100 billion years in the future, galaxies will pull apart. The universe will be made up of isolated stars, which are running out of energy. Some will become white or brown dwarfs. Others will collapse into neutron stars or black holes. Then, thousands of trillions of years after the Big Bang, even the black holes will evaporate, and all matter will decay to its basic ingredients. Atoms will fall apart, and even protons, the building blocks of atoms, will decay.
Most likely future is perhaps the most dismal one, where the universe becomes cold and dark and empty.
As the universe continues to expand and the galaxies speed apart from each other, space will become empty and dead.
Our own cluster of galaxies will be moving away from us faster than the speed of light and will disappear from the night skies.
Eventually, everything will just sort of wind down, and that's the end of things.
Finally, the universe will die, and all that will be left is a cold, dark, and lifeless space.